begin with a word of prayer. Heavenly Father, we thank you for this morning. We thank you that you loved us first, even when we didn't love you, Lord. We thank you for your grace and your salvation. Just pray that you be with us this class. Help us to just understand what we're going over. And I pray, Lord, that you be glorified in what we do. In your name I pray, Lord Jesus. Amen. All right, so just to give you a look ahead, my plan basically this week is to cover something called differentiation under the integral, and also variational calculus. And so there'll be problems, not too many problems on differentiation under the integral. I'll show you how that goes. I'm not sure I have any very good, I'll see if I can find a good homework problem to put on the next mission there. And so variational calculus is more interesting, I think. And so we'll talk about that. And then there's fall break, and then after fall break we'll have a day for questions, and then I think the Thursday after fall break we'll have an in-class test. I was thinking about like having a test anytime during the week, but I think it'd be easier for everybody involved if I just make it during class time. You all have that time open, and I won't make it too long. Somehow I will not make it too long. I like it, yes. That's why I'll probably put a take-home portion on it so I can ask something boring that, I wouldn't want you to write out in class, but you could write out in the comfort of your own bed or rocking chair, whatever it is whatever you use. I just gave away our vomit chair. Did I tell you guys about the vomit chair? Yeah, I told some of you about the vomit chair. There was an incident, and then it went outside. And I poured a good cup of grease lightning on it and lots of water, but I decided after that it was an outside chair. Somebody wanted it, so fine. Take it. I think so. I think so. They were warned it had been.
Really bad vomit,
Quantity. The quantity of the vomit which was what was staggering. And it's got it's one of those chairs that has the pull-out feet, and then it's got like that cloth that connects the feet to the chair, and there's folds. There's recesses, and there was a puddle. It was. I was going to tell you guys about this the other day, but that day Michael walked in here. I was like, he was talking about his stomach and stuff. So I behaved. He's not listening now, so it's safe also.
What was the origin?
What?
What was the origin?
I have kids. I'm not going to rat out my kid.
Yes, you are.
No. Okay, so we have most people do not have children expressly for the purposes of making fun of them, though. I think that might be.
Not most people.
I'm not most people, but I'm also not that guy. So it's a year.
Well, I have a
Pathological what?
I'm pretty sure I have a pathological view of vomit. I
Mm.
haven't been around it in a while, but I'm like terrified of it.
I see. Okay, I'll try to, well, tell you what, I was going to write this out, but I think that's foolishness now that I don't have the paper to look at me. So if I don't have the paper, then I'm just going to be like running over here, writing over there, and it's probably better if we just look at it together. What's that? I need.
Have you got your
Yeah. I mean, of course, I got up at 5 this morning and went to the Y, like every day. But
Wait, really?
wow.
Like, why
You don't pay any rent, do you, Nathan?
I pay rent.
I mean, you do?
Yeah.
But
That's why I have a job, so I can pay rent and buy food.
But I feel like with Michael, you could just be like, no, the rent is blah. I pay that too. And you'd be like, really? And you'd be like, yeah. And then you'd be like, okay.
Still pay something, right? You can't be like, yeah, the rent is zero.
No, I do not go to the Y at 5 every morning. Come on.
Seven is variable.
What? Oh, come on, really? Oh, man. All right.
It's like art.
It's
You don't understand it, but it means something.
fine. The board. Now, I will skip his super easy example here at the start, which is basically, look, it works. Well, actually, let me just show you. Actually, I will almost skip it. I'm just gonna. Actually, can you point at the screen for a second here? I'm not sure it's. I don't want to write this one out. It's not that interesting. So, of course, this is Keith Conrad's differentiation into integral. It's one of his blurbs. But here we look at a function 2x plus t cubed squared. And if you integrate that from 0 to 1, you've got this, right? Now, you can actually integrate that because this is a pretty simple function, right? So you get 1/6, I think, 2x plus t cubed. The fundamental theorem of calculus, value it from 0 to 1. You get 4/3 plus 2t cubed plus t to the 6th, right? That's just integration. Now, on the other hand, you could think about differentiating this integral, right? You could differentiate this. What would you get? You get 6t squared plus 6t to the 5th, right? So what's the advantage of that? Well, I mean, it's not quite clear yet, right? But here you could say if I take the time derivative of the integral, it becomes a partial derivative when you bring it inside, because inside you have a function of two variables, x and t. And you can, of course, differentiate this with respect to t, and it would give you what? It would give you like 2x plus t cubed times 3t squared, right? So you could pull the derivative inside, that's the claim, and do the differentiation first and then integrate second. You're like, well, okay, I guess you could do that, right? I mean, I guess it begs the question, can you do that? Is that a theorem of analysis which is known? Can you bring derivatives? If you have an integral over x, right, and you have your integrand depending on some other parameter t, can you bring the partial derivative with respect to t inside the integration? Is this allowed? The answer is sometimes. In fact, here, come on. So here's the, he brings the time derivative inside, differentiates it with respect to time, does the integral, and he gets 6t squared plus 6t to the 5th. Apparently it does work for this example. All right? So you're like, well, that's lovely, but, I probably should tell media services this lamp is dying. They look like that right before they're dead, completely.
Is it just like the bulb on
Oh, I'll forget. Yeah, that's almost written in stone. Yes. So here's an example. I'm sorry. What was that question? What? Oh, not important. Okay. So here's a question. How to integrate the following. So we want to look at the integral of. We'd like to show that the integral from 0 to infinity of x to the n e to the minus x dx is equal to what? This is Euler's integral formula, right? Turns out this is n factorial, right? Well, I mean, that's the question, is how do you show such a thing? Well, let me show you this little argument by differentiation under the integral technique. So here's the technique. So we start out with the integral from 0 to 1, integral from, 0 to infinity of e to the minus x dx is equal to 1. All right. That you can prove calculus 2 style, right? And then he's like, okay, so for any t greater than 0, let x equals to tu. Let x equal to tu. If you do that, we have what? Integral from 0 to infinity of e to the minus tu. Let's see, what would dx be? Well, yeah, but we're taking t as a parameter. T is a constant with respect to, so it's t du, right? So, yeah. So I get t du. And that's still equal to 1. And then he's like, okay, so repackage that if you will, by instead looking at this as the following. He says what you really have is the integral from 0 to infinity of e to the minus tx. Dx is equal to 1 over t. So he's changed from u back to x again, all right? Just a dummy variable of integration divided by t, right? So the first step in using differentiation under the integral is to take some problem that you know, like say this one, and kind of like, or also this one, and try to, well, I guess it's not at all obvious why this is at all connected at the moment, but you try to find some parametric family of integrals which is somehow related to the problem at hand, all right? I lost a foot on my computer, and ever since then it has been very likely to overheat. I really need to, got to put something under here, otherwise it will all of a sudden shut off on me, which would be unfortunate. Okay, so then what? What do we do? Differentiate. So differentiating this both sides with respect to time gives what? Ddt, right? Of the integral from 0 to infinity, e to the minus tx dx is equal to ddt of 1 over t. So if you bring the integral, you see what we're going to be able to do. This gives me integral from 0 to infinity, partial t of e to the minus tx. Now I'm using a theorem, which I have no intention of proving today. Okay. And then what's this? What's the partial derivative of e to the minus tx with respect to t? Yeah, minus x e to the minus tx dx. So you get rid of the minuses. What do you got? You got integral from 0 to infinity of x e to the minus tx dx is equal to 1 over t squared. If you set t equals to 1, what do you get? So we just obtained the integral of x e to the minus x dx without integrating. Through the knowledge of this one fundamental integral, right? Well, we took one fundamental fact, we did a substitution to kind of like introduce a parameter, right? Once we have a parameter for once we've parameterized the fundamental integral, then differentiating it gave us another one. And then what do? Differentiate again. What happens if we differentiate this again? So again, the derivative on the left-hand side brings down a minus x, right? So we get integral of x squared e to the minus tx dx is equal to 2 over t cubed. I'm just actually differentiating that, so I get a minus from both derivatives. Then you set t equals to 1. What do you get? Two times 1, or otherwise known as 2 factorial. Or what? Or 2, fine. And I think you see where this is going, d dt. Next, we get integral of x cubed, e to the minus tx dx is equal to minus 3, and there's a minus here, minus 3 times 2 over t to the fourth. Set t equals to 1. We get integral of x cubed, e to the minus x dx is equal to 3 factorial. This is the technique of differentiation under the integral.
So are we using that like above equation to prove that, or are we using the lower equation to prove that?
We are. This is our goal. Goal is to find this.
You weren't actually using any concept.
Nope, we have not used. The only thing I've used here, the input to this method, is what what I'll make in. It's the thing that's exploding. That's the input. And also this theorem that I haven't proved, which says that you can bring a derivative outside the integral, inside the integral, for an integral which depends on a parameter.
You can make a partial in and out.
Mm-hmm.
What is the sometimes part of that?
Mm.
With that not explained here?
No, we'll get to it. Yeah. Do you see it? Now there's this great quote from Feynman at the start of this. I will read you a slightly edited version of this quote. I'd learned to do integrals by various methods shown in a book that my high school physics teacher, Mr. Bader, had given me. It showed how to differentiate parameters under the integral sign. It's a certain operation. It turns out it's not taught very much in universities. They don't emphasize it. But I caught on how to use that method. And I used that one bleep tool again and again. If guys at MIT or Princeton had trouble doing a certain integral, I'd come along, try differentiating under the integral sign, and often it worked. So I got a great reputation for doing integrals only because my box of tools was different from everybody else's. And they'd tried all their tools out on it before giving the problem to me. Now, if you study theoretical physics, there's this thing called Feynman integrals. Like Feynman is well known for having done these just unbelievably technical integrals you could never touch with what we teach you in Calculus 2. But this technique, it will just unravel things. It's any integration which can be done and fails the techniques of Calculus 2, it's pretty much either this or the method of residues we teach you in complex analysis. One of those two tools. Kind of our go-to next level integration. Closed form.
So what we did here
Mm-hmm.
is we did Fourier we took something.
I guess I can allow a question. Yes, go ahead.
We took something similar to what we wanted to find, found an answer for it, and then extrapolated it through to find what we wanted.
Right. Now there does have to be some input. This input is, I mean, I could derive this, and I mean, how do you derive that? Integral of e to the minus x dx is what? It's minus e to the minus x, right, plus a constant. So if you integrate from 0 to infinity of e to the minus x dx, what do you get? Minus e to the minus x evaluated from 0 to infinity, but the exponential at minus infinity is 0, so you're just left with 1. Omitting some limiting arguments.
Yeah. So where did we chose that input because it looked similar?
Because it's related to this, but yeah. Oh, I think knowing how to parameterize, how to find a parametric family related to the problem at hand is the art.
Okay.
I don't think that I'm going to answer that. I mean, I will show you more examples. Maybe you can get a sense of it. Let's look at another. The best way to answer your question is to give you another example. So let's see here. See if I make sure I choose the right example. I'll just follow this blindly. I'm not sure I want to do this one. This one's kind of a mess.
That makes it different now.
This one's nice. Suppose we had the integral from 0 to 1. This is what we want to calculate. Integral from 0 to 1 of x to the t minus 1 over the log of x. Dx. So first of all, the thing to observe about this is, well, actually this is not what we're trying to calculate. This is the parametric family. What we're trying to calculate, let me tell you, our goal is to calculate the integral from 0 to 1 of x minus 1 over log of x. Oops, sorry, convert my logs to natural log of x dx. He uses the, I guess the Mathematica notation, like he'll write log 2 instead of, I'm writing ln of 2 because that's my custom, but he's actually got log, log. All right, fine, whatever. So that's the integral we're after. And apparently looking at this parametric family of integrals is the way to go. All right. Okay, so if you look at this, is this a what kind of integral is this? Is this okay? What's the problem here? I mean, these look like they might be improper, right? Because natural log of 1 is what? 0. Natural log of 0? Negative infinity, right? But the way this integration, I mean, it turns out it's not. If you analyze the, it's not actually improper. It's just like it's continuous. It's just kind of hidden, or at least that's true of this one. Okay, so if we look at this, if we differentiate this, what do we get? Let me call this thing big F. So what's partial t of this integral? Let me just go ahead and say f prime of t is equal to the integral from 0 to 1. Let me bring the differentiation inside the integral, right? So what's that? Say it's well, no, but notice that the you're thinking of like t to the something. It's not a power law here. This is the variable is the exponent. Yes, it's natural log of x times x to the t. This is like, what's the derivative with respect to x of a to, or t of a to the t? It's natural log of a times a to the t. It's an exponential function. The variable is the exponent. X is serving the role as the base. So this is natural log of x times x to the t divided by natural log of x. Well, isn't that convenient? So you see the logs cancel. Yeah, and you're just left with integral of x to the t dx. Now what you were thinking would be right. So that would be what? That's x to the t plus 1, right, divided by t plus 1, evaluated from 0 to 1, which is what? Right. right, so what we just found then is that df dt is equal to 1 over t plus 1. Now what we're actually after is the big F. We want the big F of t. So we just found a simple differential equation that satisfies. Can you solve this differential equation? I mean, you can, right? Integrate both sides. What do you get? Natural log of t plus 1, right? Plus some constant. Yes, all in good time, all in good time. We have a... I think that may be the next step, Joe. Let me just give me a second here. So yes, so let's collect our thoughts. What do we have? We have the integral from 0 to 1 of x to the t minus 1 over the natural log of x dx is equal to the natural log of t plus 1 plus some constant. The question is, what's the constant, right? So what he says is, let t approach 0 from the right, and you obtain what? Right, because we have the integral from 0 to 0. So that gives us, that implies that c is equal to 0. And then, on the other hand, if you let t approach 1 from the left, he actually analyzes that there, and he argues that in fact it's bounded by t from the left, and so the integral on the left also tends to 0. So anyway, we can argue c is equal to 0, and so what would we have? Let me erase my... There's a little bit more in the paper. I'll of course give you guys a link to the paper I'm working out of here. It's free. Actually, Professor Conrad has many of these papers on different topics, especially number theory. He's got a lot of number theory, and you can learn a lot from his. He calls them blurbs. So if you put t equal to 1, what happens then? So apparently c was 0 by analyzing the limit of t going to 0 or to 1, or both maybe. So what do we get? We get integral from 0 to 1, 0 to 1 of x minus 1 over ln x dx is equal to natural log of 2. And you notice that we computed this definite integral without actually computing the integral of 1 over the log, right? So that's pretty fantastic. Why is my computer not charging? Is this a mirage? Is this not actually plugged in? What's going on here? Why is my computer not charging? I'll tell you, this room is out to get me today. Ha! All of a sudden, my computer would have been dead in about 15 minutes, and I've been like, no!
That was really weird. Just like right before the lecture, like the projector is perfectly fine. Did he just knock it away?
So, yeah, so what's the deal? Is it a problem of the lecture? I don't know. Who cares? Let's go on. That is the opposite of what I want to spend class time on. No offense. But all right, let me try to... All of campus falling apart? Yeah. Curses. Well, anyway, if you read the paper, there's about 10 other examples, and they're all very similar to what I just did. Some of them, the end game and how you discover the parametric, how you work it out. It's different in each example. There's like a lot of analysis and stuff in here, just like kind of calculus 2 on steroids. And there's a, but here's the counterexample. Here's a place where doing it without thinking breaks down. So if you have, you can prove that the integral of sine x over x from 0 to infinity is pi over 2. We'll prove that in complex analysis a little bit later this semester. Okay, we get it from residues or something. It's a fun example. And then, so you could look at that as kind of a parameterization. You could parameterize it by introducing ty like this. And if you do that, then if you differentiate both sides with respect to t, a y pulls out of the integrand, cancels the y downstairs, and you're left with cosine ty dy. And of course, the derivative of this with respect to t is 0. So you get that this is 0, but that's nonsense. So here's an example where if you try to differentiate under the integral, it breaks down. It gives you something which is not true. All right. In fact, if you think about it conceptually, switching the order of integration and differentiation, what is integration? It's breaking up this function into lots and lots of little pieces and adding them up, right? You're taking the limit as the number of pieces goes to infinity, and you have this partition. You're dividing it more and more and more finely. On the flip side, differentiation is what? You're taking a difference quotient. You're taking the limit as the difference quotient goes to 0, right? These are wholly separate limiting process, right? There's no reason that you should be able to do one first and then the other conceptually, if you think about it. How can they be interchanged? Well, in order to interchange them, you need some condition on the integrand. Basically, you need some sort of uniform continuity, but it's a little bit more than that. You need some mild convergence conditions on the integrand. And those are not met by this thing. This does not fit the criteria. I have been vague about the criteria, but it's in this paper, which I'll post, guys. Although, so here's the theorem. No, this is not in the notes. This is a paper. I mean, it's a blurb. This is a standard technique. Don't be that way. I have found this in advanced calculus books before. It doesn't happen to be in Edwards. Everything else in the kitchen sink is in Edwards, but not this, as far as I know. Then again, it's probably in his integration chapters that I haven't studied too carefully, if I had to guess. He's back. Okay, so the conditions, it turns out you need that f and the partial derivative of f with respect to the parameter are continuous functions of two variables, and in the range of integration, and t is in the same interval around t naught. And you also need to be able to bound the function and the derivative in such a way that these integrals separately converge. So it's kind of like, if you've had complex, it's kind of like they're dominated by functions which integrals converge. And although a professor I knew here, and he's left, said that this can be improved a little bit. And I have a separate standalone proof from him. I'll also post if you're interested in the proof. It's got epsilons and deltas and the rest. And here's he actually has selection of the let's say dominating functions which converge for each of the examples that work in this paper. I showed you this one, and I showed you this one. I showed you example 2 and example 7. But as you can see, there's 1, 2, 3. There's like another. We could easily spend the whole class going over his examples. But what's that? But I'm not going to do that. What? There's something else that we'll cover today, which is more interesting, yeah? Well, I mean, this is interesting, but wouldn't you rather that I assigned you a homework problem which was solved in the paper as opposed to making up one on my own? Process that.
We had the one Not necessarily.
That is the first edition of that book. There are some typos. That is true. I'll tell you this. If you're working in problem 36, it is so very important to assume the parallelogram identity is true for the norm. If you don't have that, there's no hope of proving it. I was trying to prove part 3 of part C in problem 36 without assuming the identity holds for the norm. That doesn't make any sense. I don't think that's clear in my current problem statement. You should assume the norm of, you should assume that the how's it go? I can't remember off the top of my head. The thing I wrote,
X plus y plus the norm of the difference of x minus y.
right.
Equals to 2 times the norm of x plus the norm of y.
That, exactly. That identity you have to assume is true for the norm that you're building the G from. That's what you need to prove the bilinearity. And I got it to work just before class, before I talked to Nathan. It's not easy to prove linearity either. It's somewhat involved. It took me a half page. And I kept trying to make everything look like certain terms, and eventually I was able to corral both of the expressions into the same type of things, and then they matched. So it's that kind of, it's not that easy. And yes, it's supposed to be plus, absolutely.
Wait, where's it supposed to be a plus?
I will send out an announcement about this, but that right there is a plus.
Okay.
Everything else is fine though. As far as I've found, the other parts are fine. It's just that plus is missing. So, all right, let me get into a more interesting topic then. So, differentiation of the integral is yet another integration technique. I wanted to show you because I think you should be aware of it. At some point in your life, you may have some harder course where you're facing integrals which are really difficult. You should be aware of this method because it's very powerful, especially if you're going really, really deep into a particular question. It's really worth your time to look further into this as it applies to whatever your application is. So I think it's important for you to see it. That's about it. I don't think I've shown you enough to make it a reasonable test question unless I kind of set it up for you, right? I could ask you to use the technique, but I'd have to kind of lead you to it. Right. Like, hint, here's a parameterized family of integrals. Assuming that you can differentiate an integral, what can you derive from this? That would be a reasonable test question in here, but that's about the extent of it, right? It's not bad. You just make a u equals natural log substitution. Oh, okay. Oh, well. I tried.
What ended up happening was you started copying one problem, then you copying the second problem, so combine the two and make it
So let's talk about the variational problem. So what is the variational problem? Something that's been maybe lost a little bit in the history of mathematics. At the start of calculus, we studied variational calculus, and if you look at the old books, and I mean old, I mean early 19th century. I'm trying to keep my computer from overheating. I really need to change computers. I'll get around to it soon. They study these problems of variational calculus, and you're like, well, what's a problem of variational calculus, right? Well, something like. Let me state a couple problems. You might have something like, I don't know, you've got some surface. You got 2 points on the surface, right? And you might ask the question, which path there minimizes the arc length for the path. Find path on M with shortest length. Right. This is the what problem is this?
Geodesic.
Yeah, this is find the geodesic. This is the geodesic problem. That's a problem. Now, why can't you solve that with techniques that you already know, given a pair of points? Let's say P1, P2.
So we don't know how to minimize something that like depends on function.
Right? Yeah, I mean, what the answer here is a function, right? So if you want to think about this as a problem of optimization, the variable itself is a path. So you know, different answer. You know, there might be here's different contestants in the game of winning. You know, those are different possible answers. Everything you would try to minimize the length, the arc length, would itself be a function. So the variable here is a function. We don't know the calculus of that yet. Okay. Now, here's a standard problem, though. A standard setup is something like this. You look at something called the Lagrangian. So it would be something like this. L of y, y dot, and t is equal to, I'm sorry, not L, excuse me, J. This is not the Lagrangian yet. This is actually what's called the action. So maybe integrate from, not t, I use x to start with, integrate from x1 to x2, some function of y, y dot, and x. And maybe I shouldn't say y dot, I think I say y prime here. I'm sorry, guys. I'll get my notation on the level here in a second. The x, right? So in this would be the Lagrangian. Sorry, this is what's, you know, something like an action principle. So J is the action. This over here is the so-called Lagrangian. The thing which is being integrated is the Lagrangian. And then the question is, so if you got this set up, right, which y makes J extremal? So how to find, let's say, y star for which J of, you know, y star prime x is extreme. That is more generally the problem of variational calculus. You've got some action. The action depends on functions that you don't know, y prime, right? The functions are functions of some independent variable x. The question then is what choice of y maximizes this action? All right. I really wish the projector was working right now. Curses. What's that? Is that working? You can see yellow? All right. So basically the idea here, guys, is to say, okay, well, I'm going to assume the solution exists, right? I'm going to assume the solution exists. And what I'm going to do is I'm going to say, well, y is equal to the solution, right? Plus some other piece, plus basically some variation in y. Use this delta symbol for the variation. Now, I can be more specific, though. We're going to say that this is like y of 0x plus, and so here's y of alpha x, is y of 0x plus alpha times eta of x. So in other words, the variation in y is going to be alpha times some little function eta. So in this picture, maybe the blue one, maybe the blue path here was the optimal one. All right. I'll tell you what, I'll make it red. So maybe the red line I'm about to draw here was the answer. All right. And so that would be like my y star, which by the way would be equal to y of 0x, all right? And then the other ones you get, like, say this one, let me just eliminate. This one up here would be y of alpha x. And to get from the answer out to there, you're adding this little extra piece, right? This is the eta, alpha eta, right? Like that. And the eta has eta of x1 and eta of x2 is equal to what? So you know you've got these fixed bound endpoints for our problem we're looking at. So you know that the eta has to, those have to be 0 is the point. So these are equal to 0. The variation, the endpoints are fixed, so there's no variation at the endpoint. So what I'm describing here, perhaps badly, is that you can trade the problem of this kind of hopeless problem about varying a function to instead looking at a family of functions. All right, looking at a family of functions around the answer being the y star, which corresponds to like this parameter alpha being equal to 0. So what I'm describing then is the action j of alpha can be rewritten in terms of the Lagrangian f with x of y of x alpha, y of x alpha prime, and x. So I've traded my problem about a function for a problem about a parameter alpha, right? And so if you're going to have the maximum at alpha equal to 0, what do you have to have? You should be able to have the derivative of j alpha with respect to alpha. If that's going to be a maximum at 0, well, the derivative with respect to alpha should be 0. It should be critical point. So that's basically it. To define the variational derivative, you look at the derivative of these families of functions. So this is the basic point is my answer. If I set it, if I parameterize a family of functions based around the answer should be a critical point with respect to the parameter. And so if I partial differentiate the action with respect to alpha, I should get 0. But on the other hand, I can partial differentiate with respect to alpha. I can bring the look what I got to do. See? I got to bring the parameter inside the integral. So I guess we're assuming that f has some nice properties like the theorem, right? So the Lagrangian has to be well behaved, otherwise that step doesn't make sense. So anyway, don't bring the derivative inside, and then you've got a partial derivative with respect to alpha of these guys. So you've got a function of 3 variables, you need chain rule. You have the derivative with respect to the first slot, the derivative with respect to the second slot, the derivative with respect to the third slot. That's the derivative, right? And then, of course, times the derivative of the inside function in each case. But the derivative of y with respect to alpha, you can see from just over here, if I differentiate this with respect to alpha, you see what happens. This is 0, and this just leaves you back eta. So partial y, partial alpha is equal to eta. See that? So partial y, partial alpha is equal to eta. Now partial y prime partial alpha would be d eta dx. Do you see why that is? If I differentiate this with respect to what's y prime? Yeah, y prime, yeah, exactly with respect to x. D dx of this would be what? It would be y prime of 0x. Sorry, y prime of 0x. The notation's a little bit sketchy here. Alpha d eta dx. Anyway, the point is, you can see that there's no alpha dependence here, so when you partial differentiate this with respect to alpha, you're left with the derivative of the so-called test function. Well, I forget. I think sometimes these are called virtual displacements, as they appear in mechanics. It's called the virtual displacement, but for us, let's just call it eta. Let's call it the perturbation. It's the perturbation about the answer. Yeah.
How could the solution not exist?
I hate to ruin my picture, but there's no path.
Like the manifold isn't continuous, basically?
Disconnected, sure. If I have a disconnected manifold, I take point one part of the manifold, another point on the other part, then I can't connect them. There's no solution. There is simply no path. Yeah, that could happen. It could be that there's paths, but there's no extreme one because the edge is fuzzy. So like you want to get to this extreme thing, but it's not in there because it's not compact. It's not closed. So like it could be just outside the edge of what you want, the maximal solution. So like there's always a better one, so you just don't attain the thing. So kind of like a lack of that kind of thing could happen. Like if I took a sphere, well, let me stop. It's like kind of like the method of Lagrange multipliers. We assume that there is a solution. We're not really worrying too much about the question of existence, because as we work out the method, we'll find a necessary condition, much like the Lagrange multiplier condition. And when we solve it, once we find solution to those conditions, we'll know just from other reasons whether or not the answer makes sense. So the more abstract question of is there an answer out there is not too much of a problem to us. Okay, so then partial x, partial alpha, well, that's 0 because x and alpha are independent for our problem. Again, we're looking at the fixed endpoint variational problem. You're like, could you let the endpoints vary? Yes. Could you let the endpoints move? Yes. There are endless variations, pun not intended, of this problem. This is just the simplest variational calculus problem. So there you have it. That's partial j, partial alpha. Now, then there's a trick. There is integration by parts, basically. So if you take the partial derivative, the derivative with respect to x of partial f partial y prime, and times eta, well, product rule gives us d dx of partial f partial y prime times eta plus partial f partial y prime times d eta dx. You guys with me on that? Everybody agree? Product rule. So what I'm going to do is use this to replace this guy. So I trade this term right here, right, for what? So this is that. So I can trade this for its total derivative minus this piece. Now I like this piece more because eta appears multiplicatively. See, when I have a total derivative piece, and I'll have this piece where eta is just multiplied. The first piece has the perturbation just multiplied by partial f partial y. You guys with me? So, continuing, so that's what we had. And now I'm going to trade this for all of that by the product rule. But here's the thing. You've got the integral of a total derivative up here. Oh, sorry, I already did it over here. Sorry, I'm behind the times. So I use the fundamental theorem of calculus to change this for evaluation of that at the endpoints, right? Now there's where it's important to know that eta of x1 and eta of x2 is 0, right? If eta of x1 and eta of x2 is 0, that makes this term drop out. Okay? And then what are you left with? You're left with all this. But you can pull out the eta, and then you're left with this condition, partial f partial y minus d dx of partial f partial y prime, all times eta. That is the derivative of the action j with respect to the parameter alpha. So it's a necessary condition that must be 0, right? But you can do this for not just one perturbation eta. You can do this for arbitrary perturbations about the answer, right? So it must be the case then that the term in parentheses itself has to vanish. So you can think about this is kind of like a partial derivative in this infinite dimensional function space, right? looking at this one alpha family, it's kind of one, alpha is the coordinate along one direction, where the basis for that direction is given by the eta. But as you go over different etas, you're tracing over all the possible different directions in this infinite dimensional function space. Right? I mean, that's my intuition for what we're doing, but that's not a proof, of course. I'm not going to prove that that's true. That's technical. I mean, you can have a whole graduate course on variational analysis where you will suffer through the proofs of these things. Okay? I will tell you this is way better than what I saw in physics. In physics, we didn't really use this idea of the parameter. We just threw around this symbol as if it meant something. And we would say glib things like, well, this is true because the variation is independent of x. Okay, but what does that mean? I mean, that was how I faced this as a physics major. I was not satisfied with the discussion. Maybe you're not satisfied either. Fine. Go take a course in graduate variational calculus to get a better derivation of this. But that what I just derived here, partial f partial y minus d dx of partial f partial y prime equal to 0, these are the famed Euler-Lagrange equations connected to that Lagrangian. Okay? So, let's look at some problems. So what should the, let's see here, let's look at a simple example. I'll start with something really simple. How about the plane? So if I want to talk about the distance between 2 points on the plane, how can I capture that in terms of an integral? How about this? That's the integral from, say, I don't know. What do you want me to do here? T1 to T2. How about this? X dot squared plus what? Oh man, I've already, I'm sorry, I've already gone parametric on you guys. Let me, sorry. We're going to assume that these points are not with the same x value, okay? So x1, y1, x2, y2. That's a shortcoming of my current idea. So x1 not equal to x2, right? So here we go. Integral from x1 to x2 of what? What's the arc length? Now, don't use arc length, right? Use the square of the arc length. That's easier, right? So what would that be? That would be like it's 1 plus y prime squared dx, right? If I integrate the square root of that, that's the arc length for a graph, right? So this is L. So the Euler-Lagrange equations say I should have what? I should have, oh man. How's it go? Partial L, partial Y is equal to d dx of partial L, partial Y prime. These are the so-called Euler-Lagrange equations for this problem, which we just derived. What is it then? What's partial L, partial Y?